We've covered momentum in general. Now we're going to consider a special situation known as conservation of momentum. In physics, a quantity is conserved if its magnitude before an event is the same as its magnitude after an event. We defined our momentum as the mass of an object times the velocity of an object. That gave us the definition of change in momentum, which is just simply the final momentum minus the initial momentum, where I is standing for initial and F stands for final. So how do we use these definitions in connection to conservation? If momentum is conserved, then the change in momentum has to be zero. Well, really, all that's saying is that the initial momentum is equal to final momentum. So if our initial is before an event and our final is after an event, then we've satisfied the definition of conservation. Notice that I said if momentum is conserved. Occasionally I'll have students tell me that they learned that momentum is always conserved. And that's actually not true. I'll give you an example. Here I have a ball and I'm just going to let it roll down an inclined table. Let's watch. Yep, that was amazing. Let's consider its momentum. So at the start, right as I let go, what was the momentum of the ball? Well, it's not moving at that point, so its momentum is going to be zero. Later on, it obviously had some speed, so it has some momentum. What would that momentum be? Well, I actually don't really care to define it specifically. My point is that it's not zero. So was the momentum of the ball conserved? Well, obviously, no, it wasn't. So when is momentum conserved? Well, like I said earlier, in order to conserve momentum, we need to have zero change in momentum. Here I'm showing the momentum-impulse relationship. Notice that this is the change in momentum. This is what we defined as impulse. So the impulse is defined as force times time, but it's equal to the change in momentum. So from this, we can see that in order to have zero change in momentum, we need this quantity to be zero. That's when we can conserve momentum. So let's spend a little time going over F specifically. So F is an external force. Now maybe you've never heard the term external force, so I should explain. An external force is any force that acts from outside of your system. This brings up a new question. What's a system? So in physics, a system is the object or group of objects whose motion you are specifically interested in. So you are actually the one who defines your system. Let's go back to my the rolling ball example. In this case, I'm interested in the ball's motion. So I'm going to define that as my system. Now let's look at the forces that are acting on that system. We have weight, which we've discussed before, and then the ball is being supported, so there's a support force. Notice that because the table is inclined like this, the support force is also tilted relative to the vertical. Okay, these forces are acting outside of my system. The weight is the interaction with the earth. The earth is not in my system. I said the system was the ball specifically. The support force is from the table, and I don't care about the motion of the table, so it's not in my system. So we call these external forces. Notice that in this specific example, the net force is not zero. The support force is in a different direction than the weight, so there's no way that they can cancel each other completely. So we have a non-zero net force. Let's go back to this slide. So remember, we needed this quantity over here to be 0 to have conservation of momentum. So what we can really say then is that momentum is conserved if there are no net external forces acting on the object from outside your system. Now that we know what's required to conserve momentum, let's just assume we have a situation in which there are no net external forces so that we can have conservation of momentum. In that case, the final momentum after an event's got to be equal to the initial momentum before an event. Well, this works out great if I have one object whose motion I'm interested in. I can just plug in mass and velocity values, and the equation is simple. But what if I have two objects that I'm interested in, and I want to consider both of their motion at the same time? Well, in that case, my system would be both of the objects at the same time. That makes it a little difficult to start plugging in numbers up here, because which masses, which velocities am I plugging in? Well, it's better to think of these quantities as the total initial momentum and the total final momentum. So the total initial would be the masses and velocities of them separately. And how we handle those is then we add them together, and that gives us our total. So I can redefine this equation up here like this if I had two individual objects that I was tracking. So then this is what we call the total final momentum, now the total initial momentum. Let's give one of these objects some motion to give us some momentum. And let's say they're going to crash into each other, and I'll pause it right there at the moment of the crash. We know that when they crash, there's going to be impact forces from the collision. So what we need to determine is, are those forces external forces? If they are, then we could possibly not have conservation of momentum. So we need to define that if we're going to proceed with conservation of momentum. Here's a good time to bring back a topic we've already discussed. Newton's third law. So we know that box 1 is going to apply a force on box 2 to the right, but Newton's third law says that every force is going to have an equal and opposite reaction force to that. So we can call those action-reaction pairs. So the reaction force would be in the opposite direction, equal in magnitude. My question, though, was, are those external forces? Well, that's why I've drawn this red outline. So those forces are from objects that are inside the system. So if the objects inside the system are applying forces, those would not be external forces. We would call those internal forces. So to answer that question, no, they're not external forces, so we're okay as far as conservation of momentum. But also notice that they actually cancel each other out. So when I think of the system as a whole, I can say that there's no net force on the system. And the key here is the term system. Individually, the net force is not 0. This box is being pushed by that box and vice versa. But if I consider them together as a complete system, then I can say no net force exists. Everything cancels each other out. Let's consider a problem with some actual numbers. So let's say box 1 was moving to the right at 4 meters per second. Notice that this combination of speed and direction is velocity. And up here in my momentum equations, I have velocity. It's not speed, it's actually, this is velocity. And in this example, I'm going to have box 2 at rest. And I'm going to define their masses to be equal. Rather than make up a number for mass, I'm just going to use the symbol m. If it helps, you can think of 1 kilogram or something like that. You'll find, I'll show you in a minute, that it's more convenient this way for this specific situation. Okay, so the motion is going to be something like this. They're going to crash, and then let's pause it right here. I'm going to give this collision a special condition. we're going to assume that the sides of the boxes were sticky so that when they collided, they actually stuck together and they stayed together after the collision. Now we need to start plugging in our values up into our conservation of momentum equation. So let's start over here with the initial values. So m1 is just mass m, m2 is mass m, so I can plug those in. And I have my velocities, so I'll go ahead and plug those in. Okay, I mentioned earlier that this is not speed, it's velocity. My velocity is to the right, so I'm going to represent that as a positive. So that's why I have a positive 4 meters per second right here. And then I've swapped the masses out, and notice that because box 2 was at rest, it had 0 initial velocity. So that simplifies down to just this. Let's go to our final situation. So my goal with this is to actually determine what is the velocity after the collision. That's where this side comes into play. I don't really know what the velocity is going to be. That's the whole point. I want to find it. But I do know what the masses are. They're just m. But I do know one special thing about this situation. I said that the boxes stick together. In terms of velocity, that means that they're going to have the same velocity. If two objects have different velocities, there's no way they're going to be sticking together. So I can at least plug in that condition so it would look like this. So I've plugged in their masses. I've given the same symbol to the velocity to illustrate that I know they're going to stick together. But I can simplify that, combine it together to form 2 times m. Remember, m is just some generic mass unit, and this is the unknown velocity of both of them together. So really what you can think of is I'm treating this as one object now that has twice the mass. So that makes sense when you look at this. That's another way to think about it, is it's just one object with twice the mass, and so now I need to find its velocity. Well, I can do that by just doing the algebra. Because this is an equality, I can do anything I want to the equation as long as I do the same thing to both sides. So I'm going to divide both sides by 2m. The reason for that is the masses are all going to cancel out. Over here, the 2's cancel out. So what I get from all of that is now 2 meters per second for the velocity of the combined masses. I should point out, I understand it's a little confusing where I have m as a meter and m as a mass. I tried to use one's italicized, one's not. It does get a little confusing. It's one of those things where with practice you don't even notice anymore. So this is going to be our final result. Let's highlight that. And what that really means is that the final speed of the combined mass is half its initial speed. To see if that's realistic or not, I set up a situation that should approximate it pretty closely. So here I have this blue cart and the red cart are the same masses. One's at rest and the other one I'm going to give a push, and they're going to collide and they're going to stick together. So let's watch and see what happens. That happened pretty quick, so let's watch that again in slow motion. You can see that there's clearly a change in speed. Whether it was exactly half, it's a little hard to tell from the video, but there's clearly a change there. It slowed down. In this kind of situation where the two objects stick together, we call that an inelastic collision. Anytime objects collide and stick together, it's an inelastic collision. Well, if this is inelastic, then what's elastic? That's when the two objects actually bounce off each other. When we get into energy, we can redefine elastic collisions in a little different way, but for now it's good enough to just say that the two objects bounce off each other. So I've set up a situation for an elastic collision. Let's go ahead and watch that. I want you to try to guess what's going to happen to the motion if the two carts actually bounce off each other. I don't know if it matters in your prediction or not, but these are still equal masses. And I should point out that the camera angle unfortunately made it look like I had a slight incline, but this was horizontal table. Okay, so hopefully you made your prediction. Let's watch that. All right. Try it again in slow motion. Was that what you predicted? The math for elastic collisions is more complicated than inelastic, so I'm not going to go through it with you, but we can still apply our understanding of conservation of momentum. Notice that the first cart completely stopped, and the second cart appeared to have the same velocity that the initial cart had. Why would that be? Well, in terms of conservation of momentum, your final quantity has to be equal to the initial quantity. So in this case, there was a complete transfer of momentum. This doesn't always happen in real life. It's because I set up a situation for a nearly perfect bounce. That's the key in this example. We can do some math to consider some other situations. Here, imagine that I have the same two boxes from before. They're equal in mass, and they're compressing a spring in between them. So they're held together by this restraint. So you can imagine that if I were to remove that restraint, the boxes would fly apart. So we want to use conservation of momentum to predict the motion after the spring is released. Let's go through the steps of plugging in our values up here in the initial momentum part. In this problem, they were both at rest, so that actually makes it quite easy. The initial velocity for both objects was 0, which means the total initial momentum is just 0. If I have several objects and they're all at rest, it doesn't matter how many objects I have, the total momentum is going to be 0. Well, we are guessing, of course, that there's going to be momentum afterwards for the two boxes. So how can I get momentum afterwards but have 0 momentum to start with? Well, the key to that is that we're discussing system momentum, not individual momentum of the objects. So if I plug in values up here, I know that my masses are just m. I don't know what those final speeds are going to be, but I don't need to worry about that right now. I'll just plug in my masses. Okay, and I simplified this, but there's really no way to simplify that. I don't know what the velocity of box 1 and the velocity of box 2 is, so I'll just write that again. And the connection, the key to this is that that's equal to 0. So I'll skip a little bit of the algebra this time, and the end result is just going to be this. So what does that mean? It means they'll have the same speed but opposite directions. The negative sign here is indicating the opposite direction, because this one has positive, this one has a negative. Okay, well, how realistic is that? Well, I set up an example here to show it. There's a spring that's compressed in between them. They have equal masses, and when I release that spring, they should pop apart. Let's see how it works. Again, it's pretty quick, so it's hard to tell, but it looked pretty symmetric to me. Let's watch it in slow motion and see if it's any better. Seems like a reasonable demonstration of what our math predicted. Here I'm going to do something similar, but this time the card on the right has extra weight. In fact, it's twice as much as the card on the left now. This is a total of twice the mass of the left cart. What do you think is going to happen this time when I release the spring? Why don't you make your prediction? All right, let's see if you're right. From the quick video, it's hard to tell, but clearly this one was going slower than that one. I don't really have a good way to measure that from the video, so let's go through the theory. This spring is actually still inside my system. Okay, I'm just assuming this system is all of this. So the force from the spring is what we call those internal forces. So I still have conservation of momentum. They're both at rest. So when I plug in my initial momentum up here, I still get 0. But I do want to point out that this time mass 2 is 2m, twice the mass of mass 1. So I need to remember that when I plug stuff in. So notice m2 is 2m, but since my velocities were 0, that doesn't really do anything, and I still end up getting 0 momentum. Over here, I'm going to do something similar to last time where I'll plug in the masses. I don't know what the velocity of cart 2 and the velocity of cart 1 are, but that's okay. I can solve for it because this whole thing is, again, equal to 0. When I simplify, I'll skip the algebra and end up getting this result. What does that mean? It means the left cart, that's V1, so I called the left one object 1. The left cart has twice the speed of the right, that's what the 2 means, and opposite direction, so that's what the negative sign is telling us, which seems kind of about what we saw from the video. Now I want to point out that these add up to be 0 only because momentum has vector properties. Normally when you add two numbers together, if they're both positive, there's no way you're ever going to get a 0. So that's why hidden inside these velocity vectors is direction. We can actually add those together to give us 0. So momentum is conserved. Even though you have started with 0, you're actually ending with 0 because of the vector properties. They're going in opposite directions, so their momentum actually cancels out as a total system, and you end up with 0 momentum for the system. That's the key. The system has 0 momentum, not the individual object. There's another way you could look at this result. If I rearrange it with some algebra, and I'll skip the steps, I could read that, and this is the same equation, it's just a little bit different. I switched it around with some algebra. So I could read that as the right cart has half the speed of the left, and in the opposite direction. Here's another example. I'm going to do an elastic collision again, so they're going to bounce off. This time the blue cart has twice the mass of the red, so you can see the extra weight in the blue cart. So why don't you make a prediction? What do you think is going to happen this time? Let's see if you're right. All right, now in that case, notice how the red cart actually bounced backwards. If you consider this from a Newton's third law standpoint, the impact force was equal and opposite, but this one had much more mass than the red one, so the red one had more acceleration. If you remember, that's the connection between that. Equal force, but different acceleration because of the mass. So it was enough to actually send the red one backwards. We could go through the math of this collision, but this is an elastic collision and it's just more difficult math, so we're going to go ahead and skip that. Here's a problem we can do. I have two boxes heading towards each other this time. One of those boxes is twice as massive as the other, and I gave them the same speed just to make our problem solving a little easier. I want to mention that I'm going to assume this is going to be an inelastic collision, so remember that means they stick together. So imagine that they have sticky sides. When they crash, they're going to stick together and stay together after the collision. So like we've done before, we'll start by plugging in what we know into the initial momentum side. Remember that these are velocities, that's key. So mass 1 is just m, mass 2 is 2 times that, so I've got 2m. Velocity 1 is positive because it's going to the right. Velocity 2 is negative because it's going to the left. Here I'm just going to assume left is negative and right is positive. If you do the simplification of that, that simplifies down to negative 5 meters per second, and there's my m, my mass unit. So that worked out because really this whole thing is just negative 10 meters per second times m. So they combine to give us a negative there. Let's go up to the other side. So we know our masses, so I'll plug those in. The reason why I have the same V's is because it's an inelastic collision, so they must be moving together. Objects can't be stuck together if they have different velocities, so I can at least say that these are going to be the same, and I'll simplify that down. If you remember our first inelastic collision, this is a similar result where now we're treating it as just one object with this velocity, but now it has 3m, 2m from the one and 1m from the other. Combines to 3m. Okay, let's do our final algebra. That's going to result in negative 5/3 meters per second. It's common to write that in decimal form, so we'll round it off as negative 1.7 meters per second. What that really means is that the final motion is to the left, so once they stick together, the combined object is going to be going left at 1.7 meters per second in terms of speed. So hopefully this gives you enough of an idea of how conservation of momentum is useful when you're, especially in situations of collision. We can't end our discussion without seeing one of the most classic demonstrations of conservation of momentum. This is known as a Newton's cradle, and I'm sure you've seen one before. This version is quite big. It has 5 heavy steel spheres. Right now, as I'm holding the sphere, gravity is pulling it down. Gravity is going to be an external force. The objects that I'm interested in are these 5 spheres, so that's why gravity is external. When I let go, that external force is going to change the momentum of the system. But when the sphere collides with its companions here, those interaction forces are all going to be internal to the system, so the total momentum should be conserved. Let's watch how that works. You can see that that momentum is transferred pretty efficiently throughout the system. Of course, if I let it go too long, it slows down due to drag and other external forces. Okay, this is the one that always gets everybody. I always want to think that the one sphere is going to get knocked clear out of the way, but due to conservation of momentum, I have to have equal mass carrying that equal velocity. Let's go ahead and take a break right here. I have one last 8-minute video segment that's going to wrap up our discussion of momentum with one last interesting example.